there should supposed to be the third exercise lab on Thursday, but I tried to switch with I tried to move to the third exercise lab to the March 1st. I'm going to have the panel review the NSF in Washington, the March 1st. So instead of missing the lecture, so GA will take care of the lab on March 1st for the third exercise lab. So I'm going to continue the lecture on Thursday, so you don't have to bring your virtual machine. Okay. But the due date for the Project Zero and quiz as scheduled, so please keep checking the Canvas to submit on time. As I announced at the beginning of the semester, I'm not going to allow any the late submission. Okay, so it cannot be excused. So please try to submit on time. There is one possibility in case you do not finish the project, so you can submit as it is, even though that's not completed. Then contact the GA. GA cannot grade all at once, right after the due date and due time. So there might be the certain time until grading, so you can resubmit by contacting the GA. Okay, so that can be excused if GA does not grade the submission yet. Then you can resubmit. So, but if you do not submit anything but just the email, I'm going to submit. Please excuse no. If I ignore your email regarding to your the excuse, then that means it is not accepted. Okay, sometimes the student ask me, can I submit can I do the late submission or the excuse the attendance, but I do not reply. So that means it's not accepted. Okay, the only exception of the excuse of the absent of your class is the medical issues with the doctor's letter. Okay, so even though you have the funeral of your family, that cannot be excused. So, but it's your responsibility. That doesn't mean that it's the Professor Lee is too strict for the attendance or the late submission. Instead, it's your responsibility. In case I understand, there might be certain reason for your late submission or the missing class, but it's your responsibility to catch up or to admit such a thing. Okay, once again, so I'm going to update the website and on Canvas. So we are going to have the third exercise log on March 1st, and we will continue the class of the Chapter 5, the process of synchronization. Today, that's the topic.
Professor?
Yes?
I have a question on quiz number 2.
Quiz what?
I have a question on quiz number 2.
Quiz number 2, why don't you bring the active class? I'm going to finish. Okay. Okay, so today, we are going to have the process management this time. So as we discussed a lot, the operating system consists of the three major parts. One is the process management, and the second part is memory management. Third part is the I/O management. So last class in chapter 4, 3, and 4, we have discussed about mostly the process, how to create, what is a process, how to create the process, and how to operate such a process. A specialized process data structure is a threat to the main purpose of the resource management in operating system is how to maximize the utilization of the resource. Also, because the computer resources are limited. Another issue is how to increase the performance of the system. So we need to pursue such two things in this chapter. So in this chapter, after we create the process, definitely we have the multiple processes in operating system. So how to, for example, so it's a simple problem. I definitely bring the marker. Where is it?
Is it there?
Yeah. This one?
Yep.
But this is
Sorry.
that one. I brought the one anyway.
I have one
So-
if you want.
So I have the extra one. So let's say this is a shared data. Okay, so whatever that is, it can be mostly on memory. So we have it doesn't matter whether this is operating system or computer system. So we have the 0. Okay, there's a one guy. So name A, and this guy is usually, he knows only the add the plus 1. Any number is incremented by 1. Okay, there is another guy, B, he is doing usually decrement by 1, so minus 1. Okay, so there is data on bulletin board. So that's almost the same time, just the same time, but there's a judge or the Professor Lee ask, why don't you do their job? Okay, so A, read the data, so just open and read the data, and B also read the data, then doing their job, then update the bulletin board. What is the final output of the bulletin board? It can be
Anything.
Anything.
Plus
anything,
One, plus one minus.
not anything. It
Plus
can be
one, zero,
0,
0 or
it can be
minus 1
-1, it can be
plus 1.
+1, right? For example, the A read the data, then +1 and update it. Then followed by B, B read the data. Okay, we don't know when the A and B read the data, just to ask them, it may take a time. So B read the data is +1, then -1, so it will be the 0. That may be possible. And also, they read the data at almost the same time, so 0 and 0. So they know the data is a 0, we know the data is 0, then the A is a little bit faster than B. So updated is a +1. Then B -1, okay? Then followed by the -1. So it will be updated by -1. So it can be -1. Also similarly, so B updated first, then followed by A, so it can be +1. So we cannot guarantee such a data that happen in the operating system also. When we have the multiple processes, they are working together. They are sharing the data, so we cannot guarantee, we cannot synchronize it's a kind of race condition. They are racing, okay? They are competing for the shared data, so we need to address such a problem. Otherwise, we are not sure what is the finite value of such a data. That is called the process synchronization. So we are going to see what is the synchronization problem, what is the general solution of the process synchronization, and also how the operating system uses such a synchronization solution, okay, in their operating system. So for that, so we are going to define the critical section problem, critical section. So we will see what is the critical section, and there are several basic solutions of such a, it was here. So then one of the basic solution of such a synchronization problem is a Peterson solution. So we will see, actually Peterson solution is not used in the real operating system, but that's the basis of such a synchronization problem. Then we will see such a solution of the critical section problem. There are 3 types of the solution that we are going to see. One is the software, another one is the operating system, third one is the hardware. So we will see not all of them, some of them we will see what each of the solution is. So that include the mutex log, the semaphore, and it can be viewed as most of the solution, all of the solution are based on the locking. Okay, whatever the lock is, so they are based on the locking, which means simply, so if A operate the first, lock this one, which means nobody can read the data, nobody can write the data.
Okay, read log or write log, then update it. Then it's guaranteed. Okay, it's a consistent. Then when A release the log, then B read the data and do their own job. -1 update, whatever. Okay, so similarly, so we can regard most of the such a critical section problem as a kind of a locking. But problem is what kind of a lock and how to use such a lock. Okay, and then so we will see some typical, the traditional problem of the classic problem of the such a synchronization. You already know the producer and consumer. Producer and consumer problem are very basic and general problem in many operating systems. Okay, we already see in the process after we create the process, there are two processes. The process 1 read the produce, and process 2 is the consumer, which means create the buffer, add the data into the buffer, and another process read the data. So the producer and consumer problem, and read and write, and some other the classical problem we will see, and there's some other example of the practical problem. So we will consider one process as the producer, another one is a consumer. These are the data structure of the producer, and producer is into the buffer, add the data until the full of the buffer, then increase the counter. Similarly, vice versa, consumer read the data, then whenever consumer read the data, reduce the one. Then, so this is it's actually the same as the example that I provided just before. So let's say that there are two operation. One is a +1, so counter plus plus, and counter minus minus. So actually, when we take a look at the instruction of the plus plus, so that is the first read the data from the memory, then copy, transfer to the register, and there is the instruction to the increment by 1. So register +1 save to the register, then the transfer such a data to the counter. There are 3 basic instructions are included in this operation, and counter minus minus is the similarly, but except there is decrement by 1. Okay, so this is an example of in case of the count. This is let's say count, and we have the CPU 0, and this is the CPU 1. Okay, each one has a register 1 and register 2, and this is the shared memory count, and the initial value is the 5. So this is the one example. Okay, so because the instruction is the atomic operation, we cannot divide, stop in the middle of process. Once each instruction starts, it will be done. But this is the operation consists of the 3 instructions. We cannot guarantee whether the 3 instructions will be done at once or not. So later we will see another solution to consider set of instruction as the atomic, the group of the operation. That is the transaction. So transaction is another solution. So that is nowadays most of the modern operating system, and many applications, including database, they are using transaction concept to solve the synchronization problem. But this is the excluding. We are not going to consider transaction. So this is one of the possibilities. So register the CPU 0, read the data and increment 1 at the same. After that, the CPU 1 read the data is the -1. So currently this is a 6, this is a 4, and update is a 6, update 4. So final output is a 4, like that. So this is called the race condition. So race condition, we have the 2 consumer, but we have the shared data. At the time, it will be the racing. So we cannot guarantee the final output of such a shared data. So that is called the synchronization problem. So we already so the 3 different cases, okay, of the race condition. Okay? These are the real instruction, so but it's not important. So case 1, final output is 6 in case the CPU 0 win the race, and case 2 is the opposite, the CPU 1 win the race. So final output is 6, and also it can be mixed, so it's the final output is 5. So we need to solve that problem. So this is how to solve that problem. The problem is the two processes. When you see the two process, there are two processes, so they are sharing the same data. That is a problem. So why don't we consider to access the shared data? Okay, that operate not all the operation among the bunch of sequence of instruction. Some of the instruction would like to access such as shared data when a process need to access, and whatever the operation is, whenever the process need to access such a data, that part is considered as the critical section. Okay, so critical section is a group of the code that access shared data, not local data, not the process, the global variable, but the shared data, mostly from the memory, or it can be from the I/O devices. But whenever each process need to access the shared data or common variable or shared library, so that considered as the critical section. So critical section is the group of code that need to access the shared data. One, groups that the instruction may cause the race condition, synchronization problem. So we need to handle such a group of not entire section. If you consider, so for example, if the CPU 0 is operating, if you lock entire shared data, no other process can access this data. So it will be kind of a hang or the stop the operating system. So only the specific instruction that need to access the shared data is called the critical section. So we are going to solve the synchronization problem only for the critical section. Okay, so in addition to the critical section, we can divide the process code into the entry section, critical section, exit section, and remainder section. So we discussed about the critical section. Critical section need to access the shared data. So when you need to, for example, we have the one bathroom. Okay, so we have the 10 customer. So 10 customer would like to use the bathroom. So they cannot use at once the one bathroom. We need to find one of the customer to use that. So at that time, the customer need to wait just before in front of the bathroom. That is the entry section. Okay, entry section. So entry section means the code, process code that the willing to access is not accessing the shared data yet. Okay, just before to access data, so inform to the operating system. I need to access the bathroom. I need to access the shared data. There may be several processes. So then the operating system decide. Actually, the algorithm. That's our goal to discuss in this class. How to select the process that can enter critical section among the customer who is going to use bathroom. Okay, how to decide? That is the synchronization solution that we are going to. The Peterson solution is one of the solutions. Okay, yes.
The critical section can be used between two different processes?
No, it's a shared data. So let's say that this is a set of instructions. This is a process 0, this is a process 1, set of instructions. So we have the shared data A here in the memory. So address is FFFF. So if this instruction need to access this one, this instruction need to access this one, the offset 111, this is a 222, is a different process. Then before the process 0 enter the access this data, that the initiate the intersection algorithm. Okay, we will see what kind of algorithm is that. For example, if customer want to use the bathroom, okay, then bathroom is I want to use the bathroom. Then we need to get the key, for example, right, to open the door. Who has the key? Operating system owner. Okay, not here, not in the process. So that part key, getting the key part is the algorithm of the entry section. That is the solution of the synchronization problem. So in broad view, okay, the abstract level is kind of locking. Can I get the lock of this critical section? So critical section is this one. This will be invoked based on the instruction that need to access the shared data. Same thing over here. But sometimes this one is currently used. Then there might be several processes stop. This process is stop. The pause at this time because they cannot access. So how many processes in the entry section? 1, 2 process is waiting. Okay. So this is not part of the process code, but it's a process structure, data structure. We will see. Okay. So this is this is the critical section when a process needs to access the data. So you can update, you can read the data, update the data, delete the data, whatever you want. Then once you are done to process this data, after you use the bathroom, you need to exit and return the key to the owner. Or sometimes you can give the key to the customer who are waiting for this one. Okay, so this is called the exit section. Then remainder section is the rest of the instruction of the process, the instruction. So the operating system define the process as if you do not consider synchronization problem, just this part and this part. Okay? Whatever they want, they can process it. That causes the race condition, that causes the synchronization problem. But to address such a problem, operating system and entry section and exit section, that is the process structure used in the operating system, yes.
What exactly is critical section? Is it a code or is it a memory?
It's the code, okay? It's the instruction that need to access shared data. Read, write, it can be the common variable, it can be the shared memory, and it can be accessed by the many processes. However, if you have only one process, or if you do not have such a shared data, all of them are local variable, there might be no problem. But in case they need to access such a shared data does not mean only the shared variable. It can be the many things, any data in the memory that can be accessed by the other processes. So that part is the critical section. So if we do not consider synchronization problem, there's no entry, there's no exit. So the operating system provides such an entry section code and exit section code. When the event, when a process needs to access the critical section. Okay, yes?
You're referring to the critical section as a general term of critical section, not the operating system object critical section.
Oh, no. This is just the read the data. Okay, so this is kind of event. So operating system, when operating system define the process structure, they consider whenever the process instruction need to access such a shared data. In other words, if any instruction causes the synchronization issue, then it's invoke the entry section and exit section. It's not part of your code. Okay, so it's the operating system provide to the process data structure that we are going to discuss. Okay, so this is a simple solution. this is a process I. Let's say that we have two process I and process D. We are going to start from the two process cases. Then we can easily extend to the multiple processes. So each process, they are doing the instruction. Do while means it's a set of instruction at the end of their instruction code. Okay. Then this part and this part is who defined? Who made this one? It's a process. It's a process, the instruction. But among the remainder section does not access any the shared data, so we don't have to worry. But in case process need to access the shared data, that which may cause the synchronization problem. So why don't we consider this one? We have the ton. Okay, ton is whose ton? Who are using the critical section. For example, if process J is, this is a Boolean, okay? It's a Boolean variable that provided by the critical section, the CS solution, the synchronization solution as a process structure. So this is a Boolean, it's not Boolean, it's an integer. Integer that specify the process. J means if ton is J is using, okay? Which means, is it true?
Yes.
Yes, it's a true. True means, can we exit, this is the while loop. Can we exit the while loop? No, we cannot exit the while loop. Why? Process J is using. Right? What if J is, so we have the same, the process structure, do while turn I. This is a process J. Okay, critical section and exit section is a turn I. And this is a remainder section while true. So when the process J finished to access the critical section, which means it's done to update this data, then leave. This is the exit code. Who provide that exit code? Not process. It's the operating system provide. It's a process structure. So this will be invoked. The turn is I. So this will be changed into I. Then do the remainder section, other the instruction code. Then at the time, so turn is right now I. I is equal to J. No, it's a false. False means you can enter exit while loop, which means enter the critical section. That's what, how, it's kind of locking. What is the lock? Lock is a turn. Okay, turn is kind of key. Who is using this one. This is the simplest solution of the critical section problem. Okay, so this is the one of the solution. Let's see. Then we need to define the solution of the critical section. So this is the simplest one. However, this cannot be the perfect solution. Why? Because we will define what is the requirement of such a critical section problem. So first requirement is how many processes can access this critical section? How many? 2? 1. So this is mutual exclusion. Only one process can access. How many customer can use the bathroom same time? Only one. So that is a mutual exclusion. Then second is, I will give the 1 minute, the 30 seconds to understand this definition. If you search the Google, like the wiki, it's probably the same statement as this one. Anyone who can explain the meaning of that?
Meaning of what?
Meaning of the second, the requirement. For me, it takes almost almost a year to understand. Because sometimes when a author or the editor, they define something problem, like the definition, they try to put all the conditions, so sometimes it's very hard to understand. Actually, it's simple. It's a deadlock free, which means, so for example here, one process, if nobody used the critical section, one process should be able to access the critical section, right? So there might be no deadlock. So we will see the deadlock separately because deadlock event is very, very critical in operating system. But you know what is a deadlock? What is a deadlock?
Two programs wait for same resource.
Same resource? I don't think so.
No. Or
I'm holding, so I have this one. You have your cell phone. I need yours, but you need my cell phone. Then waiting each other, right? That's the deadlock. Okay, it's lock. It's a deadlock because there is no solution until I kill him, or vice versa. Or I'm generous, so I will give to this one. But operating system is usually very greedy. They don't want to release the resource. So it's a deadlock. So if deadlock happen, it's a stop, no matter what the types of hardware or operating system you use. So we don't want such a deadlock. It's a deadlock-free algorithm. Okay, which means that in case this one is empty, so which means nobody used the process and not in IC, because we are not going to consider the process who are processing this part, right? They may not cause the synchronization problem. Only among the processes, some process who wanna enter, who wanna use the shared data, then they will not be locked. Okay? At least one of them should be able to access this. That is, so I think this is the best way to understand what is the progress. Deadlock free, no deadlock situation. So that if you read the definition of the progress requirement of the critical section, so if no process is executing, no process in case there is process that access this one, nobody can enter because of this mutual exclusion, right? So that time, some process wish to enter critical section, right? Then only those processes that are not in, because we are not going to consider remainder section, okay? Then can decide the next one. At least one process will be, not at least one process will be able to access critical section, okay? Then that selection will not be postponed forever, okay? And the bounded time, it will be selected, okay, for that selection. So then we can understand what is the progress. The other requirement is, it's okay, this cannot be postponed indefinitely means it's a selected process. To select the next process, if it takes infinity time, then nobody can access the critical section. So the statement indicate that selection process will be done within limited time, bounded time, in the finite time. This one is a requirement, but it's the same thing. 30 seconds. Right, let's try to understand. It's just plain in English, but easier than second. It's this starvation free, which means if any customer want to use the bathroom, so if you give the priority, no, that's not a good example for to use the priority. We don't know. But if we consider just the priority of these are the process in the entry section. Okay, then this one we consider, for example, priority level 0 to 10. This is a 10. All of them is a 0, 0, 0, so this one may not get the chance. That is a starvation. Starvation is always the problem of priority-based solution. Any priority-based solution has the same problem. It's a starvation. So to address that starvation, we consider sometimes aging. Aging means sometimes later, priority will be upgraded. So something like that. So this one, if there exists a process who want to access the critical section, eventually in the bounded time, bounded waiting time, that process will be selected. So this one and this one is a different meaning. This one is a selection will not be the forever. Okay, selection is said. Then at least the process, eventually any processor will enter the critical section bounded waiting. Otherwise, it's obvious actually. So definitely only one process can access the shared data, and the progress should be the selected, and any process can access the shared data. So this is called the three requirement of the critical section problem. So based on this one, we will see whether our solution is good or not. Okay. There are three types of the solution of the critical section problem, synchronization problem. Software solution, we already see. So this is a software solution, right? We can check who is the next one, using the ton variable. This is the software solution. Hardware solution, so we make the device instruction. So CPU provide, we are going to use the CPU instruction such as the swap or the specialized instruction we are going to use. So hardware solution, definitely this one is fast. So that is used a lot in the current operating system. And even operating system provide. So software solution and the operating system solution are similar, but the operating system solution use some operating system, the built-in data structure. Okay, so like the monitor or the mutex log, mutex or the such a thing. So even though this is the data structure provided by the operating system, so we will see each of them. First one is a software solution. So we already see the similar one before. So we can quickly check the. It's also we can consider two process cases. So this is our entry section. Okay, this is the solution. This is the exit section. Critical section, remainder section. Why is just a CS and RS? Because it's a programming the instruction. Okay, process instruction. Then if the instruction access a shared data, that is considered as a critical section, then this will be invoked. Okay, then we will check this one. Then let's see. Process 0 the process structure as we have the one variable, shared variable. This is a variable for critical synchronization solution. So ton, as we have seen before. So ton 0. If ton is 0, okay, then P0. This is a 0. P0 can enter is a critical section. Okay, if process I enter the critical section, ton is I. Okay, something like that. So then let's take a look at this one. Then we can easily understand. So we have the process 0 series of instruction. We have the process 1 series of the instruction. Then we have the one shared variable for synchronization problem solution. That is a ton. So first, process 0, this instruction would like to access the shared data, so would like to end the CS. Then currently the initial value set as the 0. Okay, it can be 1, then we can check this one first. And also at the same time, process 1 would like to access the shared data. It's the same in share the data, they try to access CS. But the turn is currently 0. Turn is not 0, which means this is a false. 0 is not 0, that means what? It's a false. False means out of while loop. That means enter critical section. Okay, so right now P0 can access this one. Then what about at the same time the P1?
Professor, what if the context switch happen after the condition is...
No, this is basically the CPU 0, then CPU 1. So why don't you consider SMP? That will be much easier to understand because we are focusing on the synchronization problem. Then it's clear, right? That is the reason the beginning I mentioned about this way. Then what if the 1? Then we need to consider context switch also, there is CPU scheduler also, and the dispatcher. Okay. Then, so this one, where we are. So this currently, who is accessing the critical section shared data? Processor 0. Okay, which means in terms of the processor 0 is in here. But process 1, if this is the process 1 data structure, process 1 is keep, this will be 1, okay? This is the turn is a 0, it's a keep looping, okay? Until when? Until, so this one is done, so exit CS. When process 0 exit, there's a exit the section, exit code is change the value of turn into 1, okay? Then, that time, this 1 is changed to the 1. So 1 is not 1 is a false. Then finally, P1 can enter critical section. Okay, so that is almost the same. It's a generalized. Okay, the solution of the previous one is called the algorithm 1. Then let's check the 3 requirement. 3 requirement of them. What about the mutual exclusion? How many processes can access? Only 1. So it's a good for the mutual exclusion. And let's take the bounded time. Okay. So eventually they will get the, in 2 process cases, they will get the chance, okay, to access the data. By what? By turn is other thing. Okay. Next. So for example, in case of the using bathroom, then when exit, the next, give the key to the next. So eventually, so it's almost okay. But problem is the progress. Progress means, so what if? Whether they can enter, the selection will be done or not. Is there any chance of the deadlock or not? Is it okay in terms of progress, this algorithm? Answer is bad. Bad means sometimes that it happens. What? In case what? It's not progress. If turn, it totally depends on the turn, right? Key. Okay? If the key is, this is a 2 process cases. In case of 2 process, it can be next each other. There are only 2 customers use the bathroom. So it's next to the other person. Other process can get it. If we generalize, okay? Generalize it. So what if we have turn is set as a 2. There is no process of 2 right now. Or process 2 is in the remainder section. Okay? Then all of them are waiting. So you cannot get. The chance no process cannot get. So it's not perfect solution. It's a simple and it provides the mutual exclusion, but progress should be careful. Okay? In case of that, even the bounded time, if the progress is if locked, then even bounded time is not guaranteed. So that is the reason if progress was guaranteed, then the bounded wait time is okay. So this is algorithm 1. There's another way. So what is the main problem of this one? We do not consider who is in the entry section, right? So if we set as a turn is 2, who is not here, right? So it can be the problem. Or even two process cases, if turn is 1, but if 1 is not in the entry section, it's a remainder section. Nobody used that key. Nobody used to access the data. In case this process would like to access the critical section again, there's no chance to access. Okay? Do you understand why it's bad? It's not forced, it's bad. So sometimes it may cause the deadlock. It's a stop. So main problem of this one is there is no, this exit does not consider any the process in the entry section. So to address that problem, there is another algorithm. So we are going to use the flag, the Boolean variable. The flag means I'm not in. So false means I'm not. So 0 means the process 0. 1 means process 1. We can easily generalize. Okay. So if this one is false, which means I'm not in critical section. Okay. In other words, if this is true, true means I'm enter this process enter critical section. Would like to enter, which means in the entry section. So we can consider who is willing to. So who are in the entry section. So we are going to define the process structure like this one. So this is the entry section. This is the exit section. Entry section. This is a process I case or process 0 in case of 2. So this is a 0 and this is a 1 and this is a 0. Okay, then you can, it will be easier to understand. So, process 0 would like to enter, would like to access such data, and the flag is true. 1, the flag means I'm not in critical section. False means not in critical section. True means I'd like to access. I'm in the entry section. Okay, then check whether other process is in the critical section 1. If this one is a false, false means other process is not in critical section, which means I can access, right? So false, false means not in critical section, other process is not in critical section, so you can get out of the while loop and finally access the critical section. What if the other process is a true? True means this one is using critical section. Okay? So true means this one is using the critical section. So it's a keep looping until when? Other process exit this one. So I'm not in critical section. It's a false. Change it into the false. So finally it can this process can enter critical section. So for better understanding, I make the same thing. This is a time, and we have the process 0, process 1. This is a shared variable of the critical section problem solution. Okay. So first, default is false and false because nobody in critical section. Then first, process 0 would like to enter the critical section. That means this entry section is, this is the entry section, okay? So it's a true, so flag 0, process 0 is a true. So I'm entering the critical section. Then how can this process enter critical section in case this one is false? So right now it's a false, other process are false. Okay, then enter critical section. This time, what if the P1, other process would like to enter critical section? So this is a true. It's set as there is a process of 1, is set as the true. Okay, then can process 1 enter critical section? Yes. Currently, we need to check this one. Flag of another process. This one is 1. true. Okay, why? Because it's already entered critical section. So this is a true. True means keep looping, cannot enter. Then until when? If this process is done, exit critical section, then this one is a false. A false means I'm not in critical section. So this is not in critical section, and so this one is the false. False means out of while loop can enter critical section. Okay? Check. Is it how many processes can enter? Only one. It's a mutual exclusion. This is the most important part. Only one process, right? The mutual exclusion is the most important part of the critical section solution. So good. And what about the progress? What if both of them are set as true and true? Okay, two process case. Can any process enter critical section?
No.
No, because it's a true. It depends on the other process state. If the other process is true, when it happened, because when they leave is set as the other false, and false means not in. False means so true means true is here. Then sometimes it's happen. There is a stop or to terminate the process. So if their flag is set as older true, then there is no way to get out of the such a deadlock. So sometimes it may be happen such a deadlock situation. Okay. So because of the bounded time, we cannot guarantee the bounded time. So this is even though this solution consider the status of the entry section, but it cannot address all the requirement of the critical section solution. What if we consider algorithm 1? Algorithm 1 has a key, right? Key is very good for mutual exclusion and the decide the next one. And this one we can consider only entry section. So we need to know the status of other process. So why don't we consider both of them? Okay? So because the bounded waiting time is among the process who are waiting for bathroom. Okay? We will select, right? We are not going to consider all students, only the few students who are waiting for the bathroom. We'd like to select the next one. So how do we know those who are waiting in the bathroom or the critical section from the flag? And how to control who is going to use? We can use the turn key. Okay, so that is the Peterson solution. Peterson solution consider both turn is a key and this is the status of the process. So both of them. So this is the just combination of the algorithm 1 and algorithm 2. And for example, this is the entry section, this is the exit section, entry section. The flag is the same meaning. Turn is who is using, okay, this one. And the flag means whether I'm entering. The false means I'm not in critical section. Actually, this is correct the information, but because of that, it caused the problem of the progress, but the true means I'm willing to access the critical section. Okay, so then when a process can access the critical section, this is the logical end, right? So if this one is a true and true cannot access it, then when this process can get out of the while loop, false and false, or false and true, true and false. At least one of them is false, then you can get out of the while loop, which means can access a critical section. Semantic of this while loop, do not try to memorize. First, try to understand the meaning of the expression, logical expression. Flag say is the other process. Okay, that is a false, which means not in critical section, because it's not in critical section. Then this one is a turn. So turn is not, J is not using. Okay, so two, either of them is a false, then can access this one, the critical section. We are using the same table. It's a time. Okay, so first we have two variables, turn. The initial value is 0 and flag 0, 1, because we are considering two process cases and both of them are false. Let's see the process 0 first. So we'd like to enter critical section. When a process enter critical section, this is entry. So process 0 is set as a true. Turn is J is 1. So flag 0 true and turn is 1. So value is like this. Okay. So check. Flag 1. There are other flag. The P1 is a false. Why? Because the P1 is not in critical section. So which means it's empty. Nobody used, so we can enter this one. And turn is not matter because it's using the flag. Either of the cases we can access this one. So right now P0 is in the critical section. At that time P1 would like to access the critical section. So we are going to learn this one with it's a process 1 case. It's a flag. The 0 is true and the turn is 1. This one is 1. Okay, and this one is the 0. Okay, so the turn is 0, flag 1 is true. So currently the value is turn is 1, flag 0 is true, and flag 1 is false. Okay, then at the time check the while condition. While condition, flag 0 is true, and turn is 0. Whose turn is that? Right now, it's flag 0 is true. Turn is 0, right? Because it's set as a turn is equal to 0. So it's a true, true, true until when? When the process 0 is exit, so I'm not in critical section. It's a false. So it's a false, so then out of the critical section. Okay, then finally enter the critical section. So let's check the requirement of that. How many processes can enter in this case? Critical section. Yes, because we consider two. Algorithm 1, algorithm 2, both of them. So definitely one process can enter critical section. Can I prove it? Yes, you can prove it. So you can check all the cases. This is the proof of this one. But I know sometimes some of the students likes the details, the cases, all the cases, but some of the students likes just the description. Either way is fine. I'm going to explain based on just the description whether Peterson algorithm satisfies with the 3 requirements. But those who want to prove the strictly, so you can check all the cases. In case process I is true, then the 3 different cases of the other is true. In case of this one is true, then check the false, turn is I, false, turn is Z, and true. Like that, then you will see the mutual exclusion cannot be possible. Something like that. Okay, but we will. So only one process can access the data. And what about the progress and bounded waiting? Bounded waiting is 2 process cases. If the progress is the solved, bounded waiting will be automatically proved. Okay, so progress the main problem of the algorithm 1 is if the turn and algorithm 1 is a turn value. If that set has a different value, there's no way. Okay, if turn is 2, we have only 0 or 1, so no process can enter critical section. Algorithm 2 cases, what if both of them are true? So because of that, so in Peterson solution, we said is a turn is when in entry section we turn as the J. There's no other the turn. Okay? Because turn is a J. I'm enter. At least one process. One of the processes in entry section will be specified by the turn. Okay? So if there is another process that will say turn is me, I'm the last one in entry section. That means at least one process in the entry section. Then flag is the change manipulated by the exit section. So in case, just in case it's a true or true, then using the turn we can decide one process can enter critical section. So it's a progress. The one process, there is no deadlock unlike the algorithm 1 and algorithm 2. Because of that, in case of two process cases, then this process is bounded the waiting time. So third requirement. If we want to prove all the cases, why don't you take a look at this line? Then there is each and every cases of the two process of the F is a flag. Okay, then the turn is the turn. So you can check whether this one satisfies with that, the critical section. So Peterson solution solved the problem. However, nowadays no operating system uses Peterson solution. Why? This is for two process cases. It's not easy to generalize. You need to check all of this one, a number of processes. Okay? So, however, Peterson solution is kind of basis of any synchronization problem. Okay? So, this is a software solution. What about the hardware? Hardware means we are going to use the instruction. What kind of instruction? So basically, as I said, critical section. To enter critical section, getting the lock. Okay? When you leave the critical section, release the lock. In terms of the interrupt, you can disable the interrupt, which means no other process can enter the critical section, right? Because it's disabled. Then when you leave, so we can consider interrupt, enable or disable the interrupt as a lock, what key. Okay? So then how to disable, how to enable the interrupt. So this is a basic the architecture, how the entry section and the exit section is working. It's kind of a locking problem. So we are going to use the test and set and swap the instruction. We are going to take a look at the instruction, the solution. Test and set. I will give the 30 seconds to understand the meaning of this test and set. This is what? This is an instruction. Who developed this one? Processor, CPU. CPU provide their own instruction also, not only just very popular the move or the load or store and increment, decrement, but also they provide their own the instruction. This is one of them, which means once this test and set is the invoked started, then it will not be stopped in the middle. This set of whatever that is, they will be the completed or nothing. So that is the one instruction. That what happened? What is that test and set? Input is what? It's a boolean, true or false. Output is what? It's a boolean. Then let's take a look at. Then, in case the input is true, Okay, and this is true. RV is true. Target is also true. Okay, then return is output of this one is true. So always true. They're true. What if false? False. This is a false. This is a false, right? And target is changed as the true. Always the target is the input value is always regardless of the value of the input. That input value is changed to the true. Okay? Then return value is RV. RV is a false. Return is the same as the input. So if this one is true, true. If this one is a false, this is a false. However, this target is the, as you can see, is the pointer, is the reference. That value itself is true. Okay? Test and set as what? True. So this target is the actually false, for example. Then output of a test and set is true. Then this one are false, same as this one. Then this one is changing to the always true. That is the test and set. Then let's see how we can use such as test and set. This is an example of that. Let's say log is false. Let's say log. Then test and set log is return of test and set of the log is what? Same as the input. It's a false. But log itself is the change it into true. This is a key. Currently nobody uses it. It's a false. So if you operate the test and set, it's a change. False means nobody uses, so I can use. Then after that, log is changed into true. So in case the other process access the critical section, which means test and set log is a true. Log is a true. So output of the test and set log is true. So it's used. It's a log. So log is still true. So you cannot use. It's very simple, but we can manage the log of the critical section. So let's see how we can use in the solution of this one. Most of the hardware solution is much simpler. Okay? So this is an entry section. This is an exit section. So log, if log is a false, nobody use, right? Output of the log is what? This is a false. False means out of a while loop, you can enter critical section. Don't pay attention to this one. There's no statement of inside the while loop. Okay, some student they're confused. Okay, then what if at this time other process would run this one, same the critical section, the solution, test and set, the log is a true. Output of a test and set is a true. So keep looping, right? So keep looping until when? So when a current process exit, so log is set as the false. So this is a false. Okay. So output of the test and set of log is a false. Then enter critical section. Okay. So this is the solution using the instruction hardware solution. Okay. There is another one using swap. What is a swap? Swap exchange the value. So this is the instruction level, which means it cannot be stopped in the middle. There are two variables for swap. So A and B, both of them are reference value. So we need the temporary space to exchange. It's just exchanging. So we can use the swap for like the one value is for key, another one is the log. Okay. So that means swap key and log, which means key is a false and log is true. Let's see how we can use the swap operation for the critical section problem solution. Okay. First, log is a false, so nobody use. Okay. So entry section is key is equal to true. Key is available. Okay. Key is available, and then if key is true, true is true. So we need to do this one. Okay. We have the statement in the while loop. It's like this one. Okay. Then it's a true and true. So do this one. So key is true, and log is what? Log is a false, right? So we change it. The value key is the false, right? Because we swap, and log is true. Then check. While loop key is false. Then this is the out of while loop, which means enter critical section. Okay. Then other process would like to enter the critical section. Right now, the key is true, and log is true. So even though swap is true until log is released. So in this, the swap solution is like the Peterson solution. So key is showing what? I'm in the entry section. Log is who is going to use. Okay, which process is using the critical section. Okay, so this is another way. Well, critical section. Then, however, this is the solution for what? Peterson solution is the same as the Peterson solution, which means even though it provides the all requirement of the critical section problem, but it's only two process cases. So can we generalize? In here, we can easily generalize the solution by defining, instead of we have the key, okay? Instead of, this is a log, kind of log, okay? The key is true, and waiting is for the managing the process in the entry section. So number 0 to 9, so it's true. So we can use the while loop. While loop is waiting. So this is the process 0. For example, process 0 case. So this is a 0, and this is a 0. Okay. Then process 0 is true. Waiting is true. So which means it's a entry section, and key is equal true. So this process is enter. So this is a true, and key is true, and then so you can do this one, okay? And test and set. You can log is of the initially false. So output of the test and set log is this is a false. Test and set is the same value as the input. Then log is actually changed into true. That is a test and set. Then going back to the while condition. And this is the key is a false, which means out of the while loop. So you can enter critical section. Then, am I waiting? No, I'm not in the entry section. So this is a false, then critical section. There might be no problem to understand this one. So currently, when you are when any process, one process is in the critical section, there might be no progress. Progress is only when there's no process in critical section. Then, when this process 0 exit this one, j plus 1 is, this is the next one, okay? j plus 1 is the any process. It can be any process, and next one. So then, why? Because we have the 0 to number of process. So this is the current process. J is the not this one and any process. It can be plus 1, the next one. So J is I plus 1, it can be. Okay, so any process, start from this one, then check. This should not be the current process because I'm not in the entry section. Among the process in the true, which means ready section, okay, then check. Then if we find, so this means the not in is a true, and this one is not waiting. For example, if the next process, J process is not in the ready section, is a false. The false means it's a true, so keep looping until this one is a true. You can plus next, check the next. So this is a false, true. False means not in the ready section. True means in the ready section. So this process will be selected. Okay, that is a waiting is a false. Then that process changes the waiting can enter critical section. Okay, so how many process? Definitely mutual exclusion is guaranteed. So only one process can enter critical section. What about the progress? One round of turn, one process will be selected. Right? So if all of them are false, not in the critical section, which means that's it, because it's no race condition. But if this one is true, the last one, next, finally this will be false, get out of this one. Then at the time, change their weighting. So the process ends process, the weighting is a false, then finally enter critical section. Okay, so progress is okay. What about the bounded waiting time? If you have the number of process, you can, this is always next, right? So at most one round of the time, it will get the chance to access the critical section. Okay, so this one provide the all three requirements of critical section. I think that we need to do the, I already explained that this one. Next, semaphore. It's a 48, right? So we will see the semaphore and the other solution and operating system based solution in the next class. And also we are not going to have the exercise lab the Thursday, just for lecture. Okay. Then the March 1st we will have the third exercise lab. I will update and send a message all the students also. Okay. Thank you.